Hi. So, hi, good evening, everyone. So, welcome back to Plan 258. Yeah. Can we start? We can open your camera. Okay, so today we discuss, well, this is still part of game theory. Yeah. And then this is the reverse game theory. Yeah. We discuss about mechanism design. And at the end, you will have your group project presentation. Yeah. So I would like to remind that you're supposed to do the student evaluation of teaching, yeah, in CLS. Okay. And these are the topic next week and the following weeks, yeah, until the end of semester. Okay. So let's start then. So back in 2010, I was going to Washington, and this is my note. I don't know if you can see. So this in this note, I wrote down the game of trust. So I started to make derivation about what is called harmonic game. Okay. So I basically want to know whether it is possible to create a society which is actually trustable. Okay, so that is our first topic there, harmonic games. So you can follow this in Moodle, yeah, the slide in harmonic game. Can you see my slide?
Yes, sir.
Okay, so in this lesson, you will learn it is non-zero sum game, yeah. So it's a strategy game, what is called harmonic game. So this is basically game of trust. Okay, and we will compare prisoner dilemma and harmonic game. While the presentation seems like very mathematical, okay, but this is the foundation for the next topic, mechanism design, okay, which is very crucial for planner. Okay. So we have learned in the past few weeks about prisoner dilemma, right? So in here you have two prisoners, Mr. Rowe and Mr. Column, being interrogated separately, and if both confess, yeah, it's sentence 8 years in prison. It would deny its sentence 1 year, and if just one confess, the other release. Okay? So the one that uh, confess will get 10 years in prison, and the other one will be released. Yeah? So this is the typical prisoner dilemma values, yeah? And we can compute mass equilibrium and Pareto optimality. So we discussed about the technique to compute this last meeting, right? So in that case, you will say play as Miss Row, okay? And so you look at the first number in the row, and then you check, you know, if Miss Row select trustable, okay, what Mr. Column will do. And then if Miss Row select cheat, what Mr. Column will do, and so on. Yeah. So eventually the equilibrium will be cheat, right? And clearly this is also not Pareto optimal. Okay? So when we say Pareto optimal, that means a state where no player payoff can be increased without decreasing the other player payoff. Yeah. What happened? Yeah. Cheat is the last equilibrium. That's correct. Right. So this is a review from last meeting. Yeah. So, and we can also actually I already showed this also about harmonic game or trust game. Yeah. So in this example, can you find the Nash equilibrium and Pareto optimality? Yeah. So you can select if Miss Row is going to hold be traceable, what Mr. Column will do. Mr. Column will uh, select between traceable and cheat, 3 and 2. So 3 will be winner. Yeah. Yes, that's correct, Lester. So it is traceable and traceable is the Nash equilibrium. Yeah. So if so this is the basically the Nash equilibrium. If we hold this one, so again it will select traceable. Yeah. Then you will select if Mr. Column hold traceable, what will be the result? Yeah. And if Mr. Column hold this to play cheat, what will happen? Yeah. So you will see, yes, Pareto optimal. Yeah. So traceable, yeah, is the Nash equilibrium and Pareto optimal. So what we can conclude with this? Yeah. So you see that there is possibility, right? There is possibility that we can change. Yeah, we can change the incentive, yeah, performance evaluation in order to create a society, yeah, that is actually trustable. Okay, so this is very important lesson on this simple game theory. Yeah. So what happened is, what is the meaning of that number? Yeah. The number means if you look at the value again, I will copy here. Let me copy this. Uh, yeah. Okay. Yeah, right. So whatever you do, yeah, they will select uh, trustable. Why? Uh, yeah, because if you lie, yeah, you will get punishment, right? And if you are trustable, you will get reward, not punish. Yeah? So this is called the right direction of control. Okay. So if you want to create trustable society, you need to change the reward and punishment in order to be in the right direction of control. Okay. Without this, people tend to go to prisoner dilemma. Okay. So now, now let us look at the more detail. Okay. What define prisoner dilemma and what define harmonic game? Yeah. So if you look at more detail, what define prisoner dilemma are these two conditions. Yeah, this is the two condition of prisoner dilemma. Yeah, so you can put the numbers there as R, R, S, T, and P here, and these are the meaning. Yeah, this is supposed to be reward, yeah, not reward. Yeah. So, so the reward, yeah, compared to punishment. Yeah, so the reward compared to temptation, so the temptation is higher, right? So then it become a problematic. Yeah. So then what make the definition, yeah, of harmonic games, yeah, or the game that actually create harmony or trustable? Okay. So these are the four condition that I found very easy, yeah, to get. So this is the necessary and sufficient condition, yeah. So if you have, so I put it this way, okay. So I have put it A, E, B. Okay, so let me put it this way: A, B, C, and D for Miss Row, and then E, F, G, and H for Mr. Column. This is like my old slide. Let me get the new slide there. Hmm. Harmonic. Oh yeah, okay, this is the better one. Okay, so the same thing, but I just color it better. Can you see the slide? Mm. Okay, can you see the slide?
Yes, sir.
Okay. Okay, so with this easier to see, I hope. So I have put the value and A, B, C, D for the row, and then E, F, G, H for the column. Okay, and then the one I put in bold is the one that we compare. And E and F, E and F. Okay, so you put E as the larger one. Yeah, and then C and A between the two rows. A is the larger one. Yeah, and then between H and G, G is the larger one, and then between D and B, so B is the larger one. Where do I get this? This is exactly uh, the way to compute mass equilibrium, isn't it? Right? So once you know how to compute mass equilibrium, so you can design. Okay, you just reverse uh, the game theory, so you can design this. Yeah. So if you want to make it more interesting, yeah, we can create invariance, yeah, of the variation of harmonic games, yeah, by adding certain condition, for example, non-Pareto or ring condition. So the point is, yeah, this four condition is basically the system invariance, so that you will create uh, trustable, yeah, in the harmonic games. Okay. Now, sometimes, okay, harmonic games is not so obvious, yeah, because if you put it only this way, okay, you will have trustable, and as the mass equilibrium and the Pareto optimal, right, a while ago. But it is possible that Pareto optimality is not always in this cell. Okay, Pareto optimality can be in other cells. Then, for example, cheat sheet can be the Pareto optimal, but trustable still be the mass equilibrium. Do you understand the meaning? Uh, Mass equilibrium is the actual behavior of the people. Okay, Pareto optimality is the system optimal. Yeah. So yeah, the rest is how I derive, yeah, the this condition. So you can read by yourself the detail on how I derive these values. Okay. Yeah. Basically, the way I derive is based on uh, how we compute mass equilibrium. Okay. So let's check this. Okay. You have the calculator of game theory, right? So you can try this value, okay, and you will get traceable, and Pareto optimality also the same set. Okay? But you can also have another variation of non-Pareto optimal. So in this case, Pareto optimality is actually these three cells, not TT, but the Nash equilibrium still in the traceable. Okay. And then the same thing with the other variation with the wing condition. So I add this one of these two condition. You will see that uh, the Pareto optimality move, yeah, can be these three cells in this example. Okay, but the Nash equilibrium continue to be traceable. Okay, so this means we can actually design, okay, a better society. Yeah. So the question is how we design, the payoff of the system into harmonic games. Yeah. So that means you reverse the idea from getting the Nash equilibrium. Yeah. So first, I start with designing what is called do we want. Okay. So say we want this AE to be the this cell traceable to be the Nash equilibrium. Yeah? So we know the right direction of control. Okay. Then we can set in this case, yeah, the other values based on what we want. Okay. Uh, so because we know how to compute mass equilibrium, so we get this condition, yeah. And then now you want to say, okay, if I know that condition, what will be the number, right? So if you want to get the number, say you want to get the integer number rather than any real number, okay, you can just set any value, yeah. So example here, you have C is less than A, right? In that case, you can set, okay, in that case, I can just arbitrarily assign the value. Okay, that means C equal to A minus 1, for example. Okay? And then the next condition, yeah, F is less than E. Then you will say, okay, in that case, I will set F equal to E minus 1. Okay? And then D is less than B. In that case, you will say, okay, in that case, B is equal to D plus 1. Yeah. And the last one also. So with this, you can have okay, the value that you can design. Okay, so this is the example. We start with this E and E, A and E as your target, right? And then you can set off, yeah. So in that case, I want to get D and H. Okay? Because you have the condition, say you set the Pareto optimality, okay, you can set the value of integer based on this condition. Yeah, this is the example of value. So because you put this, so you set this value here, yeah, D and H there, and then you continue, okay, to design the next value. Yeah. So based on the C less than A and F less than E, then you set these two values, okay, and so on. Yeah. Eventually, you will get all depends on certain variables. Yeah. Once you get all these variables, this is the last value. Which is depends only on the value of the Nash equilibrium, it is A and E. Can you see that? Okay. So in that case, because we already know this value, then you can just set any value here. Okay. Then the rest is just -1, -2, and so on. Is this clear or not? Do you get the idea? Okay. The idea is you have learned about game theory, right? So now you want to design the reverse of game theory. This is called mechanism design. Okay. So how are you going to reverse the game theory? Yeah. That means you want to control the system that you design. You want to do planning, right? So in that case, you need to set the goal. Yeah. The goal is your Nash equilibrium. So in this case, trustable. Okay. And then you find the condition in order to get this trustable become your Nash equilibrium. Okay. And then from there, you can do algebra in order to get this kind of value, which depends on the cell of Nash equilibrium. Okay. Once you have this, then all you need to do is just input A into any number that you want, E into any number that you want. Then the rest is just follow. Is this clear? So any question about this? So the rest of the slide is just designing other variation of this. Yeah. So here I want to design variation, okay, of harmonic games, right? So and then I set this as non-Pareto. Okay, so this is the variation. So then based on that, of course, the condition change. Okay, then you can set the value. This is just algebra. Yeah. Finally, you get this value, which is depends on the Nash equilibrium. Okay, and then you can just fill up this A and E number. So you will get another set of harmonic game, yeah, that the Nash equilibrium still traceable, okay, but because this is non-Pareto, so you will see that this is not necessarily the Pareto optimality is not necessarily traceable. So in fact, this yellow part is the Pareto optimal values. Is this clear or not? Did you get the big picture? Okay. The detail of computation you can study on your own, okay, because the slide is with you already. But the big picture, can you get the idea? So you can design what you want. That's the big picture there. Okay. By knowing the computation of Nash equilibrium, so you can get that. Okay. Okay, with that, the rest is just other variation. Yeah. So for example, Oh, this is interesting, yeah. So, uh, what if I want to design harmonic game that is zero-sum game? Is it possible? Yeah. Actually, this is oxymoron, yeah. So trust actually implies mutual benefit, yeah. So that means you need to have strictly non-zero sum concept. Yeah. But you can try, okay, what happens if you insist, yeah, I want still to have zero sum game. Yeah. So using algebra, then you can disprove. Yeah. So that actually, if it is zero sum game, you cannot, yeah, create a design mechanism for trust. So uh, the rest of this is just the proof, yeah, the algebraic proof. We start from here because this is zero sum game, so you need to put that A and E is just minus, isn't it? Okay, so E is supposed to be minus A. So this is the first condition of zero sum game. Yeah? And then from there, you check, yeah, if it is Pareto optimal possible or not. Yeah, so if you want to have zero sum, then H and D must be also negative to each other. Yeah, but that violate the Pareto condition. So it is not possible to become Pareto optimal in zero sum game. Okay, and then let's try non-Pareto condition. And then you will see also that even non-Pareto condition, yeah, is also impossible, yeah, to get that what we want. Yeah, so this is the continuation of the derivation, yeah, and eventually you get the values, yeah, this one, right? Eventually you get the values, but what's the problem here? The problem here is now cheat become exactly the same as your trustable. Yeah. So what is the meaning of this? That means, okay, the Nash equilibrium is not trustable, but both trustable or cheat. So this is just to disprove, yeah, with simple algebra, yeah, that even if you attempt to build trust in a zero-sum environment, yeah, this is conceptually contradictory. Yeah. So if you want to create true cooperation, that's the point. Yeah. If you want to create true cooperation, you should not make them in the strict zero-sum game. That's the lesson there. Yeah. So attempt to build trust in zero-sum environment is conceptually contradictory. Yeah. There is another way to simpler than that to prove by contradiction. Yeah. So these are the other proof. Yeah. Based on the system invariance a while ago. So you can see that this is also not possible. Yeah. And then we can also have another variation. What if the harmonic game is actually symmetric? Yeah. So is it possible to do symmetric like that? That's very simple, yeah. So this is the condition for symmetric. So, and this is the examples of symmetric harmonic games, yeah. If you ask the AI to generate harmonic game, most probably they will produce symmetric like this. Yeah. Not the other variation, yeah. Okay. So what is the okay, so Is this symmetric or not? Is this symmetric or not? Yeah, if you want to get symmetric, you need to test this condition. Okay, so clearly this is yes and this is no. Yeah, not symmetric. So how are we going to apply these harmonic games in daily life? Yeah? So many application. Yeah. So this is not just abstract theory, but we can actually design, yeah, robust and trustless system. Okay. You don't need to trust each other automatically become trustable. Okay. Because you design the system. Yeah. So a few uh, of the application I listed here. Okay. So one example is traffic enforcement through camera. Yeah, so using camera system, okay, by installing the automatic speed camera, okay, and of course you need to put very high punishment if they are speeding. Yeah, so then you can guarantee they will obey based on this simple system. Yeah. So how does it work? Yeah. So you can check the uh, based on game theory. Yeah. So the speed camera will actually remove the dilemma whether to speed to save time or to guarantee to get the fine, which is worse than the time save. So this example of the values. Okay. Based on this example of the values, so then people will obey the limit, yeah, the speed limit, because uh, the other side is guaranteed to get worse. So for transport planner, okay, traffic is actually personal dilemma. Yeah, you want to save time by speeding, right? So, but if everyone doing that, then uh, the problem is everyone will speed and there is a traffic accident may happen. So then you need to reverse the directional control. Yeah. Say, for example, by installing automatic camera. Okay. And together with the strict uh, fine, okay, then it will create a system that actually penalize, yeah, if they do speeding. So another example that often used in commercial is escrow system, yeah, and reputation, right? So e-commerce, yeah, like Shopee, yeah, Airbnb, uh, and eBay, for example. So creating this trust, yeah, or harmonic games, okay, based on escrow, yeah. So without the platform, okay, the buyer will uh, cheat the seller or the seller will cheat the buyer. So this is a personal dilemma, yeah, because temptation to take the money, yeah, and not ship them is also high. But by setting, okay, the reward to pay and to ship is actually higher, yeah, than to cheat or to scam, okay, then it will guarantee the people to move toward the direction of control. So what you need to do is to change so that cooperation become dominant and rational strategy. Yeah? So this is the example of the K matrix. Yeah. So if they pay, the buyer pay and the seller ship, Okay, so this is the similar to trustable, right? So this is the mass equilibrium. Okay, so but if they don't do correctly, okay, if they bypass the system or did not ship, okay, the money that they escrow will be taken by the system. Then it is uh, guarantee, yeah, refund, for example. Yeah. So with that, people will move toward trustable cooperation. Okay. So the mass equilibrium and Pareto optimality in this set. Okay. Is it clear or not? Any question? So another example, okay, is corporate compliance. Yeah. So of course, this is also dilemma. If the company actually doing uh, fraud, for example, so the employee will have some dilemma whether to report or not, right? So if they report the fraud, they can get fired from the company. But if they don't, okay, so there is also dilemma. Yeah. So in that case, you, for example, the SEC, yeah, can prevent the collaborative fraud system, okay, by creating what is called whistleblower bounties. Okay, so the regulator can issue a massive fine to the company and then offering multi-million-dollar bounties to the whistleblower. So by shifting the game matrix, okay, then you can create better system. And this is the example of the game matrix. Yeah. If you report, yeah, you will get better value compared to if you cover up. Is this clear or not? Any comments? Any uh, discussion about all of these topics in this slide? So nowadays with the uh, smart contract, okay, you can also say using blockchain. Okay, so you can also use blockchain or smart contract, okay, using cryptography, yeah, to make the uh, trust, yeah, to validate, okay, the possibility so that people will not cheat. Okay, so using system that you have created, okay, so the trust is actually not required as human emotion. Okay? So you can enforce the trust through uh, cryptography condition, yes, so that people will actually cooperate rather than cheating. Okay, now this is actually has been used in Bitcoin, right? Okay. So the point now is game theory works, yeah, in reality, in practice. So now what you need is actually to design. Yeah. So you can create better family, yeah, better office, better city, yeah, if you uh, assume everyone is actually having self-interest. Okay? And you can find uh, engineer the variation of these games in order to go to your right direction of control. So, any discussion about this harmonic games? What did you get from this lecture? So, any discussion? Any question? Okay. So in the next slide, so you can download the mechanism design. The next slide. Okay. Can you see the slide? Okay. So in this topic, I think this is quite a lot, more than 100 slides. So the idea is you want to have compliance or trust or good behavior to make your system work. Yeah. That system can be traffic network, can be certain plan that you want within the city. Okay. How you will build the system, okay, so that you can produce optimal desired outcome. Okay. So we are going to go into more detail, and that's harmonic game. That's harmonic game is the foundation of this. Okay. So we want to make where people want to cooperate. Okay. And why smart people often make decisions that actually hurt the team. Yeah. So you will also see we will use the game theory and mathematics, yeah, to understand why this happened and how to fix that. Okay. So these are the part, yeah, that we will discuss in this topic. Yeah. So first is the problem of trust. So this is the game theory, and then I will introduce you with the mechanism design. So how we engineer the root. Yeah. And then we go more detail, yeah, about several topics, yeah, principal agent problem, moral hazard, information asymmetry, and so on, yeah, until market design. Okay, so my goal by introducing you with all this jargon or terminology, that means you can start to search on your own, yeah, in Google it or you use AI, yeah, to search this terminology. Then you can design. Okay, I understand nowadays you have AI. Okay, but at the same time, if you don't understand the correct terminology, right? So when you ask, you will not get the one that you want. Okay. But once you understand the jargon or the terminology, then you can actually use this more efficiently and more effectively. Do you get it? Okay, let's start. So I will start with the foundation of game theory. Okay, so I want to argue here that game theory and mechanism design is actually uh, two sides of the same coin. Okay, in game theory, uh, you have the rule of the game, right? The game matrix, right? And then you want to predict the behavior of the player, which is the Nash equilibrium. And you want to know, okay, what is the best for the system with this Pareto optimality, right? So this an example, okay, given the free road, how fast will it jump? Yeah. So traffic congestion is basically Nash equilibrium. Because everyone is selfish, so then they will go to almost the same route at the same time. Okay, so mechanism design, okay, is the reverse of game theory. Okay, so given the desired outcomes, what do you want with this? I call it right direction of control. Okay, then you will design the rule of the game. You will make planning. If I want to go zero congestion, yeah, zero congestion, what will be the congestion pricing of the toll, for example? Yeah. So the basic idea is you can reverse, yeah, the game theory in order to uh, find the structure, rule, and the incentive, yeah, so that uh, the agent or the individual that is rational, okay, they will lead to what you design with the social optimal. Okay, so now to understand the system failure, okay, we will start with what is called prisoner dilemma so that you will see this. Okay, what is the actual problem? Yeah, people tend to compete. Yeah, even if you actually gain more from cooperation. In fact, several weeks ago, yeah, we play this game, right, prisoner dilemma game, and the whole class go to the lack of trust, isn't it? So in every interaction, yeah, you will choose either to compete or to cooperate, and we assume that you do not know how the others will behave and you cannot communicate. Yeah. So this is mean simultaneously without knowing the other people's choices. Yeah. Because of this information gap, so the trust actually break down and will lead to suboptimal outcome. Okay. So let's take example of these two persons, Alice and Bob. Yeah, they are developing. Yeah, they are the two developer in critical project. Yeah, so say either for a project of creating a software or any project that you want. Okay, so if both of them actually cooperate, yeah, you will get this value. Okay, but if one of them actually exploit the others, okay, the one that exploit will get more than uh, the one that cooperate. Okay, but if both of them, okay, uh, exploit to each other, then the project fail, yeah, without any bonus. Yeah, this is common in corporate work, right? And you know this is personal dilemma, right? So if the two of them cooperate each other, okay, they will share like say 50-50 bonus. So this is 5 and 5, right? So if one cooperate and the other one okay, just being lazy. Okay, so the one that cooperate will gain 2. Yeah? Okay, and the one that did not cooperate, yeah, will get the one that compete will get 8. Yeah. So these are the actual prisoner dilemma in the real world. Okay, so that's why performance evaluation matter, right? So what happened is we know, yeah, that the mass equilibrium of prisoner dilemma is compete, right? So this is a problem. We don't want this to happen, but because of the competition, okay, so then the teamwork will not actually have any trust to each other. So then the question is, can we actually increase the trust among the team member? How are we going to create a system that is actually controllable? Yeah. So back to harmonic game, yeah, it is possible, right? So we can build the society, yeah, uh, when the liar are punished and trustable people are rewarded. As simple as that. Okay. So in theory, this is okay, right? Then the question is, what happened in practice? So yeah, we know, okay, this is the best, but in practice, this does not happen, right? Okay, so we know what is the right things, but we do not do, right? So we know teamwork is essential, okay, but the conflict between the team, okay, create a reward structure that actually destroy the trust. Okay, so that means we cannot rely on goodwill. Yeah, we need to design the evaluation of performance. Yeah, to do what is called mechanism design. Okay, so what is mechanism design? Yeah, this is the second part. Yeah, so remember, yeah, we cannot change human nature to make people less selfish, isn't it? Yeah. So, but we can change the environment. Yeah. We can engineer the economic. Yeah. So we can stop asking people to do the right things. We can create the system. Okay. So the method is go backward. Yeah. So instead of predicting how the system will fail, yeah, now we create the rule of the game. You create a system. That's actually your job as planner, isn't it? Hmm? So first you decide what is the desired outcomes. Okay? After that, you design the rule, the incentive, the punishment, okay? And the constraint. Okay? And assuming that everyone is having self-interest, okay, then naturally they will go into this outcome that you design. Okay? So these are several terminology, okay, that I want to introduce. First, we have what is called principle. Okay? Principle is you, the designer. Yeah? Can be the government, can be the company, can be the platform. So we call this principle. And then we have also term agent. Yeah? That means any individual with certain information and self-interest. Yeah? When we say mechanism, that means the rule of the game. For example, voting system, auction, and so on. And then we have some function, yeah, to map the agent input, which is the strategy, to the outcomes. Okay, the step is simple. So first, you have the goal. Okay, so I call this the right direction of control. Yeah, what is the goal? That you are the one who set. Yeah, for example, efficient pricing, fair allocation of resources, and so on. And then you design. The step two is you design the incentive and the punishment. Yeah, that can be money, can be reputation, can be access, can be just praise, and uh, just word. That's okay. Yeah. So uh, motivation or discouragement. Okay. So, and then you design this incentive and punishment to ensure that the truth telling or the right direction of control, the desired behavior is actually the best strategy. Yeah. So in design mechanism, you find this keyword, Fikre auction. Yeah. So Fikre auction is uh, bidding, okay, still bidding. Okay. And say you want to maximize the bidding, uh, then you get if you win the bid, you don't pay that highest value, but you actually pay the second price. Yeah. By making this, actually you create a mechanism, yeah, design mechanism that will make the bidder reveal their true valuation. So because bidding higher or lower does not improve their payoff. Yeah. I'll give you another example here. Yeah. Say in hotel room, yeah, if you just say, please don't forget to turn off the hotel room. Oh, this rely on goodwill. Yeah. This is certainly will fail. So then you engineer the rule. Okay. You don't rely on human memory or goodwill. So you can ask, okay, using the card, the key card slot that required to power the room. And nowadays, hotel room is also already using this. Yeah. So this is align self-interest with the system goal, isn't it? Okay. By environmentally choice architecture, yeah, that use physical constraint. Yeah. Then you force the compliance. So hotel room that require your key card to keep the light, yeah, will guarantee the zero energy waste when you leave. Is this clear or not? Yeah. So enforcing this constraint to the physical layer, okay, is usually superior, yeah, compared to just asking goodwill. Is this something interest you? Okay. But creating a mechanism design have many challenges. Yeah. One of them is called information asymmetry. Yeah. Why? The agent may lie. They might hide their preference. Yeah. There is also a possibility of complexity. Yeah. So it can be both fair but practically difficult. And there's possibility that the agent may cooperate or collude to each other. Okay. So, and there is a trade-off between efficiency and fairness, simplicity and robustness, and so on. So there are certain trade-off that you need to balance. Okay. So what is information asymmetry? Yeah? These are the two hurdles. So when you design a system, yeah, these two massive hurdles. Yeah? First, people know more about their situation than you do, right? So the problem is they will lie, yeah, if it is benefit them, yeah. So the second is to fix your system, yeah. Then you need to have incentive compatibility, yeah. This is a strict mathematical threshold. It means that even if a user is completely selfish, the most profitable action, yeah, they can possibly take is to follow your rule, yeah, to tell the truth. Yeah, is actually better than to lie. Okay, so you need to design this. Yeah, so if you ask, say, a developer, what is the true cost? They probably will lie. If you ask the citizen whether they want to pay for the park, yeah, say you want to pay, create a public park, they probably will lie because they need to pay. Yeah, this is information asymmetry because you don't know, yeah, whether they lie or tell the truth. Yeah. So your job is actually to design this, yeah, incentive compatible mechanism. Yeah, to set the rule so that lying become mathematically less profitable than telling the truth. Yeah, this is the core constraint. Yeah. So uh, is this clear or not? Yeah. So this is say we want to do right direction of control. Yeah. Before we write the new rules, right? We want to identify the reverse. Yeah. So why the old one failed? Yeah. What is wrong direction of control? Yeah. So in principle, you want to get what you measure, yeah, what you reward. Yeah. Depending on the reward system that you create, yeah, okay, how you measure it, then you may have wrong direction of control or right direction of control. Yeah. So example, yeah, in healthcare, yeah, if you want to be healthy, uh, right, as your right direction of control. But the problem is the doctor are paid when you are sick, right? So in that case, is it uh, within the self-interest of the doctor to make you healthy or to make you sick? Huh? The same thing, yeah. In say you want to ask developer to do software, example software contract. Okay, we want fast and clean delivery. Yeah, but when the contractor are paid by hour, yeah, then it is within the self-interest of the programmer, yeah, to uh, to prolong their hour, right? So efficiency will lose because of this system of contract. Okay, so here are the example of wrong direction of control. Yeah. So if those who do violence get praised as hero, defender of justice, right? Those who cheat, tell lies, do certain crimes, get praised as being smart. Yeah. So, and this is actually encouraged by children's story. Yeah. So children's story, if they create moral story to the children, okay, it will go up to uh, mature or adult. Okay, so they will think that cheating is okay because they are smart. Yeah. The same thing, those who get rich out of corruption, pollution, yeah, get appointed as leaders. So this is wrong directional control. Yeah. And those who say honestly will get blamed as being rude or undiplomatic. Uh, okay. Similarly, people or country that actually flee the war perceived as peacemaker. So my question to you, let's discuss. Yeah. Can you state other example of wrong directional control that you have known or experienced? Anyone? Do you get the meaning of wrong directional control and right directional control? Anyone have certain ideas, certain examples? Daniel, you want to say something? Yes. Thomas, I don't get your message.
Yes, sir. I was watching this movie, The Interpreter by Nicole Kidman and Sean Penn.
Okay,
And there was this character of a certain African country, the president. He framed himself with his head of security to be assassinated. But before that, that head of security shot the one who's about to assassinate, so that he will be framed in the picture of the media and the UN as the one who is the hero.
I
So
see.
rather than being framed with what he did for that particular country.
I see. I see. Yeah, thank you. And Daniel, what do you mean by this?
I think one common example of this sentence is that poor people are lazy, therefore they are poor, but it's not a straightforward correlation. So sometimes their unproductivity, which is perceived as laziness, is actually caused by a lack of opportunity, which causes them to be poor. I think apart from that, another example that I can imagine is how Filipinos are more likely to go to malls rather than parks. So, uh, people say that their parks are neglected because people don't go to parks, but it's because uh, it's malls that are much more dominating the metropolitan landscape in cities. So, in that way, so malls are more attractive and
Then
also
talk
in turn
about.
neglecting parks. So,
Okay. So Thank you. Any other example that you want to share? Right. Okay. Yes. George, can you say it so that the others will know?
Okay, sir. Hello?
Yes, yes. Oh,
Hello?
yes, yes, George.
Okay.
You go ahead.
Okay, sir. I think, sir, I can share about our education system, what I chatted with you, sir. That our education system, the goal is for students to learn and understand the concepts. However, our system often rewards those high grades instead of really understanding the topic or the concept itself. So the
Mhm.
students only focus on memorizing only the answers that will be given to the exams
Oh,
instead of deeper understanding of the concept itself.
okay. So that's also problematic, yeah? So later you need to design, okay, to reverse this problem, okay? Okay, Lester, you want to say something?
Yes, hello, Prof.
Yes.
In terms of wrong direction of control, on a daily basis, with regards to the existing traffic enforcement here in Metro Manila, to be specific, since we as commuters we want safer roads and fewer violations, but the current system in the Philippines, they are rewarding those traffic enforcers who caught more violations.
Mm.
Then instead they should do something to prevent these violations to occur, sir.
Okay. Okay. Paul.
I think one relevant example is social amelioration in the Philippines.
What is
So, for context, sir, our government has this program called 4Ps, on which they are incentivizing the poor by giving them monthly allowances by virtually doing nothing. And here's the catch: the fund for that program is actually taxed on us, the working class.
Oh.
So one perfect example now, the uh, prices of
Mm.
electricity generation is uh, currently increasing due to the crisis on Middle East. And part of the tax that we pay on our electricity providers goes on to those group of people. So in short, I think it is a wrong direction of control because we are essentially incentivizing the non-working class group of the people while this incentivizing the working class and those who are really working hard for the economy.
Okay. Okay. So then, yeah, there is also, Diane, you want to say something?
Yes, sir. Regarding the four-piece, they are actually with the Paul's statement that they are doing nothing. That's not the case. So for four-piece, the program is incentivizing the poor to actually capacitating them into becoming a human capital. So not necessarily it encourages laziness, but programs kagaya I like in Pasig City, they are really have this monitoring and evaluation that the programs, especially directed to 4Ps, are productive and the city also gain from it po.
Okay. So,
So just a clarification since
okay.
there's an ongoing friction between the middle class and the lower class, so lower than the middle class, so the marginalized basically. And then actually not all of it comes from our own taxes,
Okay.
but also from most of it comes from VAT. So VAT, yung 4Ps also pays that VAT through their food, and other services that also requires us to pay the VAT. So basically, hindi lang sa atin nanggagaling, or it does not come from us, from our withholding tax. So most of it come from VAT, which also paid by the marginalized people. So yun, sir. Just
Oh,
clarification.
that's fine. Yeah. So I have no comments. Okay. Okay. We just discussed about this, and then later on, I hope you can reverse. Okay. The wrong directional control into the right directional control. Okay. So there is also discussion, for example, wealth tax. So that means this is actually wrong directional control, because those who work hard to accumulate the wealth will be punished, while those who spend more will get incentive, for example. Yeah. So, okay, so let's go to the simple math. Okay. What is the meaning of reversing directional control? So you simply invert, okay, the payoff structure, yeah, so that the actor profit will be strictly coupled from the system success. Okay, so let's say you have the current flow, okay, is Y. Yeah, this is the incentive structure. And then if you want to create the new design incentive, yeah, then let's call this X. Then X can be either one of these technique. Yeah, one is just flipping the code. X is just minus of the Y, or you can use it by relative value. Yeah, so we call this relative ranking reversal. So you invert the payoff relative to the maximum amount. So you get the maximum of the Y, and then you minus the Y, yeah, to get the new value. Yeah. So mathematically, actually, rather simple. Yeah. So what is the right direction of control? Right. So the right direction of control means you want to get the things that you want, right? So in principle, you want to reward the behavior, okay, and punish that behavior against it. So this can be a set of performance evaluation. Yeah. So you make it in such a way so that when people behave in that direction that you want, okay, they will get reward, not punishment. Okay? In the other hand, if they don't behave in the direction of our control, then they will get punishment, not reward. Yeah. So this is mathematically simple, but it's a tool. Yeah, that means depending on who use the tool, yeah, can be make it in the correct direction or in the wrong direction, depends on you. Yeah. So the wrong direction of control would happen, yeah, when the system inadvertently reward the problems. Okay. So this is actually a feedback loop design. Yeah. So positive feedback applied to the error state will cause the system spiral out of control. So you need to invert the sign a while ago. So I write here, strong defense is the same as strong attack. Okay, so to do reverse directional control, okay, given a system, so you need to use paranoid technique. So we call this threat modeling. So the terminology in design mechanism is called threat modeling. Yeah. So you need to identify all the adversarial edge cases. That means you need to list down all the possible cheating scenario paranoidly. Yeah. How the rational actor, yeah, will will exploit this mechanism, including collusion with the internal or external agent. Okay, first you need to and list down all the possible problems, the threat. Okay, and then for each that scenario of the threat, then you start to create the robust reward and punishment system, yeah, to prevent that cheating scenario from happening, even if everyone is actually selfish. Yeah, they can be designed to be trust each other. Okay, so there are several tools that you can use. One is feedback mechanism. So using performance evaluation. Yeah. Other tools are monitoring. Yeah. So you do tracking. Yeah. So when you do monitoring, it's very important that you remind them that they are still in the game. Yeah. That reward and punishment still in the game at all time. Yeah. And the third tools that you can use is verification mechanism. We will discuss this later in the next part. Yeah. So here is the third part of mechanism design, yeah? So that we can create the core logic of this. Yeah. I want to introduce you with two terms. Yeah. One is called principal agent problem, and the other one is moral hazard. So with this, you can start to talk about this jargon. Yeah. So what is principal agent problem? Yeah, this is actually the hardest problem in management. Yeah, principal agent problem. So this is a structural conflict of interest. Yeah, the principal is basically the owner, the clients. Okay, that will hire the agent. So the agent here is the worker, the contractor, to do some task, isn't it? So you hire the agent to do certain job. Okay, so the problem is your goal is mathematically opposed, right? So there is a conflict. The principal want maximum quality for minimum cost. The agent want to have maximum profit for minimum effort, isn't it? So there is a conflict of interest. Yeah, you want them to do work hard, but they want to work less. Okay, so if you write bad contract, okay, depending on your agreement, you will create what is called moral hazard. Yeah? Like Paul was telling a while ago, right? So moral hazard means you end up paying for their laziness, yeah, for their mistake, yeah. So moral hazard is a specific failure state, yeah, where the agent will take excessive risks or act lazily because they are not the one who bear the responsibility, not the one who bear the consequences or the value. Yeah, it is the principle that bear the consequences. So this is a moral hazard problem. Yeah, so I put here. So it's a specific state of failure. Okay, when the agent, yeah, will take excessive risk or act carelessly, yeah, or they will reduce the effort basically, yeah, because the one who bear the financial or systemic consequence is not them, other person, yeah, the principal. So this is delegation problem, isn't it? Yeah. So when one entity, which is the agent, yeah, is delegated to make decision on behalf of the other, the principal, right? And then there is a conflict of utility function. Yeah, the incentive is misaligned. So moral hazard will happen, okay, when you remove the physical consequence of action from the person or the actor who performed it. So be careful with that. Yeah. So when you subsidize a failure, you guarantee its occurrence. Okay. So let's take certain example. Yeah. So the principal is the client. The agent is the contractor. What the principal want? They want high quality, right? Low cost. What the agent or the contractor want? They want high margin, low effort. Yeah. So I put here in the table. Yeah. Say some of you are architect, yeah, design the building. Yeah. So then you also need to design the contractor to build them. This is actually a principal agent problem. Yeah. So if you use, say, fixed price, yeah, fixed price contract, what happened? Yeah. If you use fixed price contract, the contractor dominant strategy is to use cheap material. Yeah. You then what to do? You need to change the contract. Yeah. So you can use, for example, share saving to align this profit with your quality. Yeah. So this is actually a classical misaligned incentive. Yeah? If the contract metric does not accurately proxy the system goal, yeah, then the agent, the contractor in this case, will optimize for that metric and then destroying the entire goal. Yeah. This is actually called Goodhart law. You can search. Yeah? Goodhart is the name of person. Okay. So if you hire a contractor and then pay them by hour, then you practically institute what is called cost plus mechanism. Yeah, this is a flow mechanism. Yeah. So if the contractor is brilliant and finish early, they will lose money. Right. So their strictly dominant strategy is to build slowly. Right. In that case, this is a flow mechanism that you should not use. So what is the better mechanism? Yeah. You have share saving. Yeah. Share saving contract. That means you set a baseline budget, say 1 million. Yeah. Then if they build cheaper, they keep half of the saving. Yeah. Then now to maximize their own greed, right? They are mathematically forced to save you the money. Correct? So, yeah, by changing the agreement, the rule, the contract, yeah, you actually align your metric to the goal. Did you get the idea or not? Yeah. So when you change the target cost with the share saving, yeah, so you align their profit directly to your efficiency. Yeah, aligning this metric is very important, right? So suddenly, the contractor wants to find cheaper, faster way to build without sacrificing quality. Yeah? Because when they save every dollar, okay, that is also go to their own pocket. By aligning their self-interest to your goal, okay, that is the inversion direction of control. Is this clear? So we can put this into K matrix, yeah. Before, you will have something like this, right? So, say example only, and this number are example. So, before you have this number, contractor will get 50, and the client will pay like 900. Yeah. And then what happen is they will inflate the hours. Yeah. When they inflate the hours, okay, they will get 100K, and you will pay say 1.2 as the client. Yeah. Why? Because NAS equilibrium is to inflate the hours. Yeah, this is you create a prisoner dilemma games. Okay. But now if you change the system, okay, with share saving a while ago, say the cost is 800, yeah, and then the contractor will get the base plus 100, yeah, if they do optimize efficiency, and then the clients will pay say 900, yeah. But if they inflate the hours, yeah, okay, the cost is 1.2, is the same as earlier, okay, but they will get penalty, okay, and the client still pay 1 million. So in that case, okay, because the contractor profit is strictly coupled with the client saving, yeah, they will behave to optimize the efficiency. Is this clear or not? Yeah, something practical, right? So yeah, I give certain example here. So yeah, I think this is the explanation of the numerical example of that table here a while ago. And you can read on your own the detail. So this is another example here. Yeah. So say you have this is the problem of moral hazard. Yeah. So the homeowner will face say 10% chance of say 100K flood. Okay. And then the expected loss is say 10,000. Okay. And then they need to spend like 5,000 on the drainage maintenance to prevent that. Okay. So this is what is called moral hazard problem. The government say want to do subsidize to this flood insurance. Okay. So then because of this, okay, the homeowner expected loss will drop to 0. Yeah. There is no responsibility for that. Then they will stop spending that 5,000 a while ago. Okay. And then the government will now pay say 50,000 for the damage. Yeah. The result is the system will subsidize its own destruction. Yeah. So I will put more detail, yeah, into numbers. Say this is the baseline. Okay. Say in the baseline, you have rational homeowner. Right? So the expected loss is the damage multiplied by probability. Right? Say the damage is 100,000. Probability to have this is 10%. So in that case, multiply, you get 10,000. And then they need to pay maintenance cost. It is 5,000. Right? So because 5,000 is less than 10,000, the expected loss, then it is rational for the homeowner to pay, yeah, that 5,000 in order to avoid the 10,000 loss because of the flood. Okay, this is the base state. Yeah, this is the correct one. Okay, now the story of moral hazard happened when the government take over that responsibility. Okay, say for example, now government kindness, yeah, they will provide free flood insurance. Yeah, this is the external intervention, which is the government insurance. Okay, that change the incentive. Right. So with that flood insurance, the homeowner personal loss now become 0. The expected loss also become 0. Okay. So what will happen? The rational choice is to stop the maintenance without any personal risk. All right. So the homeowner logically avoids spending on the prevention. Yeah. Then what is the result? Yeah, there's no maintenance. The flood probability will rise, say, from 10% to become 50%. Okay, at this point, the government will pay 50% times the 100,000, so become 50,000. Okay, the outcome become 50,000 burden to the system compared to that 5,000 prevention. Do you get the idea? So the idea of moral hazard is by removing the individual financial risk. Okay, look like you're very kind, helping the people. Okay, so the government actually destroy the structural incentive for prevention. Okay, and this is guarantee of massive systemic loss. Yeah, the government unintentionally increased the cost by undermining rational incentive. Right. So remember this, yeah. You may be kind, okay, but kindness without systemic foresight can unintentionally create more harm than good, right? So the harm can be greater than the problem that you trying to solve. So if you have good intention, that must be paired by good system. Otherwise, you actually create engineering catastrophe. Yeah. So the lesson learned from moral hazard is, okay, when you protect, yeah, to remove certain responsibility, then the system will collapse. Yeah, under the weight of unintended consequence. Anything to discuss about this? Any example that you already know about this? Yeah. So this is another example, yeah, of a principal agent problem. Yeah. So the principal, the clients, want the highest quality, say, software delivered, yeah, in shortest time, in for the lowest cost, right? But the agent, the contractor, is paid by hours. Okay, what happened? They are incentivized to increase the billable hours, isn't it? Whether they are intentionally or unintentionally. Okay, okay, this will create slow delivery, yeah, and financial risk. Yeah, so the system matter, because this is actually a moral hazard problem. So how to solve this? You change the contract. Yeah. So you create responsibility to the agent to absorb their own cost of inefficiency. Okay. So if you use hourly rate, okay, the contractor revenue is strictly tied to the amount of time they spend, right? In this case, efficiency will reduce. Okay, the last equilibrium is actually they want to do inflate the hours, yeah, instead of doing the uh, work efficiently, right? But if you change the milestone, yeah, become a different way, yeah. For example, now the contractor is paid flat fee for delivering the milestone, the working milestone. Okay, then the profit margin is now fixed fee minus the cost of their own time, isn't it? Right? So in that case, when they do inefficient, yeah, then that risk will be transferred, yeah, to the contractor, okay, to the programmer. Okay, so now you change the Nash equilibrium, yeah, the dominant strategy flip, yeah, toward efficiency. Okay, so then they will behave, yeah, because the contract changes, isn't it? So you don't need to micromanage them anymore for them to work faster. Yeah. So the design mechanism will force them to do it naturally. Yeah. In 2008, yeah, in the US, I think to Obama, yeah, there's a problem in the bank at that time, okay, because they are too big to fail bank, right? So because the financial institutions know that the government will bail them out to prevent the economic collapse, okay, then the dominant strategy is actually to create a high yield catastrophic bet. Okay, so they will keep the profit if they win, and the taxpayer will lose if they fail. Yeah, this is the example of the game matrix. Yeah, so before the bailout guarantee, there is no moral hazard. Yeah, so look at this. If the economic is stable, the bank will earn modest profit if they do safe bet. Okay, and if they do risk bet, the bank will earn high profit. Okay, and then if the economic collapse, the bank survive with limited loss. Okay, but if they do highly risky bet and the economic collapse, the bank will fail. Okay, the shareholder will lose everything. Because of this, there is no moral hazard because they are the one who responsible, right, for their own failure. So then the bank will internalize the both gain and loss. The best choice for this game matrix is to do safe bet, yeah, because otherwise the catastrophic will wipe them out. Yeah, so the Nash equilibrium is to safe and low yield bet. Yeah, carefully calculated risk. Okay, by after the bailout guarantee, meaning the government will absorb the catastrophic loss. This is actually introducing moral hazard, right? So when the economy is stable, it's the same, but when the economic collapse, okay, doing risky bet, the bank will survive with bailout. Yeah, the taxpayer will absorb the losses. So this is basically moral hazard. Okay, so then what is the dominant strategy? What is the Nash equilibrium? Yeah, of course they will do risky bet, yeah, because they don't. Anyway, the government will pay out using taxpayer money, right? So the system fragility increases, yeah, because government intervention. So be careful. Many of you are government employees or planner. Okay? So when you do planning, so create a system, check first. Is there any moral hazard possible using this system? Okay. So what is the lesson learned from this? Yeah. So when the actor are shielded from the consequences, yeah, the dominant strategy become reckless, right? So without systemic accountability, yeah, the safety net will turn into an engine of catastrophe. Yeah. So you need to engineer the rule, yeah, so that the decision maker personally completely unhindered before the taxpayer attacks. Okay. So you need to align the selfish desire with the self-preservation, yeah, so that the public desire is go to the stable economy. So this is the example that I mentioned a while ago about healthcare system. Yeah, in the current healthcare system, when you get sick, you need to pay the doctor, isn't it? Then it is within the self-interest of the doctor that you get sick. But our goal is actually to have healthy population, right? Okay. So what is better direction of control? Yeah. So when you're healthy, you pay certain insurance. So you have third party or the doctor itself. And then when you get sick, actually you're supposed to stop paying the insurance, yeah, for receiving the money from you and need to pay for your health costs. Yeah. Then it is within the their self-interest, yeah, or the insurance to keep you healthy. Yeah. So you reverse the direction of control by paying the insurance when you are healthy, okay, and the insurance pay when you are sick. Yeah? So the incentive become health. Yeah. So we can put this into game matrix, isn't it? So in the first here is actually moral hazard. Yeah. So the doctor is paid when the patient is sick. So what is the Nash equilibrium? The doctor will wait for the patient to get sick, isn't it? Yeah. So they are reactive. Yeah. But using insurance model, yeah, the doctor or the insurance will pay a flat fee while the patient is healthy and then absorb the cost when the patient is sick. So then they will do preventive, yeah, not reactive. Okay. So by changing the game matrix, yeah, suddenly the doctor or the insurance highest paying strategy is to call you to the preventive checkup. Yeah, it is within their self-interest to keep you healthy. Okay, is it clear? Now, a while ago, I talked about threat modeling, yeah, paranoid identification. Yeah. So what is threat modeling? Yeah, definition. So threat modeling is systematic, yeah, paranoid identification, how the rational actor will exploit your rule. So finding vulnerability, yeah, structural vulnerability, possible attack, yeah, before your system is deployed. Okay, so remember, you need to assume, yeah, everyone is selfish by default. Okay, and then you need to list all possible cheating scenario paranoidally. Okay, is there any possible external collusion? Is there any possible internal sabotage? Yeah, and then, yeah, for each of the scenario, you create the prevention. Yeah. So by listing all these possible cheating scenario paranoidly, then you can list down also the possible prevention. Okay, so do not assume that the user will follow happy path. Yeah? So threat modeling is very important tool. Yeah, so that you will view your mechanism that you design purely as a target. So then you need to map out, yeah, all the input, the output, the actor, and then check every possible exploitation. Okay, you need to design. So I throw this. So say you have the system description that you want, right? You assume everyone is selfish. Then you list down all possible path scenario. Yeah. So you think about your opponent from your opponent point of view, yeah, paranoidly. Yeah. Okay, and then for each of these scenario, you list down the prevention. Yeah, you reverse the direction of control. Yeah, you reverse the possible bad situation. With that, you have a trustable, yeah, reward and punishment system, isn't it? Okay, so I give you example. Yeah? Carbon credit. This is the usual example. So, say the government want to introduce certain green energy vehicles based on, say, battery weight or something. Yeah. So by doing threat modeling, then you start to suspect, yeah, probably the factory owner can bribe the inspector, probably, yeah, to double their reporting emission reduction. Yeah. Why? Because the bribe cost is just 10,000, okay, and the value of fraudulent carbon credit is 250,000. So it will become massive ROI. If the cheating, yeah, is actually massively positive, then the system will be breached. So then you need to create a design mechanism to change this. Yeah, probably you need to create a system, automatic monitoring system. Yeah, to increase the cost of the attack. Yeah. So yeah, remember, yeah, doing threat modeling, that means you need to find the possible adversary. Yeah? You need to find the possible threat. Okay? That what they will do in order to achieve their selfish ambition. Okay? So the threat is they will not build better battery, yeah, because of the subsidy. Okay? So then they will build highly inefficient, heavy battery, yeah, using cheap material in order to maximize the subsidy extraction, because you base it on weight. Okay. Another example here is common, probably in the Philippines, is the security guard problem. Okay. Say, if you create the contract, yeah, say, imagine you are a rich person. Okay. So, and then you create a contract. If the security guard cuts the criminal, then they get big reward. What will happen? Then they will fake, yeah, catching the criminal, okay, get more reward simply by cooperating with the criminal and the police, right? So be careful. There is possibility of cooperation among the agent. So then the criminal will try to disturb that rich man or you, yeah, to get the cuts, send to the police, who will even though they cuts, and then they will release the criminal again, right? So as the result, okay, you will receive more petty crimes. Okay, so how do we reverse the direction of control? Okay, what is the goal? Yeah, what is the goal? The goal is to have no crime, isn't it? If the goal is to have no crime, then the contract should be tied up with the metrics, right? Then you will say, if no crime experienced within certain time period, okay, then yeah, the security guard company will get certain reward, say yearly reward or something. Okay, so that's the design mechanism. Yeah, but there is another problem. If you do this, there's another problem. What will happen? The problem is they will hide. Yeah, yeah. Paying for no crime will introduce a new failure problem. What? They will suppress. Yeah. Even if there is a crime, they will suppress the information. Right? So if you just reward based on zero crime, yeah, then they will suppress or hide the evidence of the crime. They will not report. So how to solve this? Right. So in that case, you need to decouple the reporting, okay, from the evaluation. Yeah. Okay. They probably will hire their someone else, yeah, to create zero crime. So in hybrid system, yeah, reward for zero crime, the outcome based, yeah, but you will also introduce heavy penalty, yeah, for the unreported crime. How do you know? Then you will create auditor, yeah. So this is what you call a while ago I introduced verification mechanism. Yeah. So you intentionally inject the fake breeds. Yeah. So for example, like marked packets or if the guard hide it, okay, they are fired because they cannot distinguish between the real crime and the audit. Okay. Then hiding the information will become catastrophic financial risk for them. Then they need to report everything. Yeah. So you still have the zero crime bonus, but with severely asymmetric penalty if they do unreporting crime. Example, you can have what is called whistleblower bounties. Yeah. So you establish a mechanism, verification mechanism, yeah, that introduce external actor to receive bounty for reporting this. I hope you get the idea. Yeah, and this is the game matrix, isn't it? Yeah, within this game matrix, yeah, it is within the self-interest, yeah, to report everything, yeah, and you may have also zero crime, yeah. So in principle, yeah, the principal and the clients intentionally hire a third party, yeah, to commit the control, independent, yeah, checking. By doing this, okay, then if the guard fail to report, yeah, even one of these injected breeds, then they will have zero bonus, for example. Okay. So is this something interest you? Yeah, you can practically design, the one that you want. But when you design it, be careful because there's possibility of moral hazard. There is also possibility of people will collude or cooperate with each other, yeah, to do certain thing that going out of the right direction of control. Then you need to do threat modeling, isn't it? So I hope in your group project, you will start to do this kind of mechanism. You need to create this kind of system. Yeah. Is that possible? Any discussion that you have? Yeah. I'm not sure if the next topic is the next example is within your self-interest. Yeah, this is about revenue sharing in the farmland. Yeah. But suppose you own agricultural land, say you want to create a revenue sharing system, okay, and then say the farmer will pay for doing the work, right? And then the goal is actually fair share, yeah, maximize the profit. But there is possibility that the farmer will actually cheat, yeah, through cooperation with the external factor and so on. So then you need to find the possibility of collusion. Okay? Probably they will lie, okay, to create fake report of the sales and so on. Yeah. So then you need to modify the contract, okay, so that it will become better. So this is actually a principal agent problem, yeah, with information asymmetric. Okay. So how do you make so that the farmer will be honest? Yeah. So revenue sharing without tracking, without monitoring, will not make them become honest. Yeah. So what you need to do is actually redesign. Yeah. So redesign so that the both win-win solution, yeah, for the owner, the landlord, and the farmer. Okay. How do you redesign so that they will report honestly without relying on the moral compass? Yeah. So then you find you go to analyze the threat, the possible problem. Yeah. So the landlord provide the land, right? The farmer do the work and the seed. Yeah. But there is a lot of possible exploit factor. Yeah. So either hidden action or hidden information, right? So if you assume all of this risk variable you cannot measure or control, then it's a problematic. Yeah. So then what is the solution? Yeah. One of the solution is fixed rent, right? So instead of profit sharing, so you can have a fixed rent mechanism. Yeah. So in this case, the farmer will pay strict flat fee to lease the land, yeah, regardless the harvest size, for example. Yeah. Or you can also decouple, yeah, the fixed price, okay, with auditing the selling of that product. Yeah. So you can make another off-take agreement. Yeah, this is called information routing. So the landlord will negotiate the fixed price. Yeah. So that the pricing and the farmer will handle the execution. Yeah, based on that price. Okay. Okay, so up to here, is there any uh, question, probably, or discussion or comment? What did you get? So when I said you need to do threat modeling, doing paranoidly, yeah, some student will say, "Oh, come on, why I need to do paranoid?" Yeah, but that's the way to do, right? Without that kind of negative thinking, you can say, "Oh, culturally, I don't want to think negatively." By saying that, practically, you are inviting the problem to you, right? So by doing threat modeling, you are not always thinking negatively. Yeah? By thinking negatively, you need to prevent that. So that then you need to think positively. Okay? So only thinking positive is practically creating a threat to you, to yourself. Yeah, you need to have both, yeah, negative and positive thinking. Okay. So next part is what is called information asymmetric. Yeah. So in this topic, I want to dissect clock taps, yeah, certain mechanism and for public good, yeah, and then we can check, yeah, what happened to free rider problems. So the term first, yeah, word is called information asymmetrics. Yeah, let's talk about the hidden action where the agent is lazy. Yeah, now we need to deal with the hidden information, okay, where the agent knows the true type, but you do not. So say you build a system that treats everybody exactly the same, right? Say average rule. Okay. By doing so, actually, you trigger what is called adversarial selection. Yeah, adverse selection. Okay. So the good user will realize they are subsidizing the bad user. Then they will abandon your system. Okay. So adverse selection is a systemic failure when you apply one rule, which is the average rule, to all segment of population. Okay. So I give you example later. Yeah. So what is called adversarial analysis? Yeah. You evaluate the threat modeling, right? Based on the human nature that they are actually selfish, right? So, and you need to identify how the rational actor will exploit the possible information asymmetrics they may lie. Yeah. Now, if you do not perform adversarial analysis during your design phase, then they will perform it during the production. Okay. Remember this, yeah. So you need to assume that the actor and the external input are not just selfish, but they are actively malicious. They may coordinate to force the total system failure. Wow, I'm teaching you to be paranoid, yeah. But this is how you do, yeah, threat modeling analysis. Okay, so you need to find a loophole. Yeah, you need to stress test the system. You need to check what will happen if, say, 51% of that actor collude. Yeah? What if the actor is actually willing to lose money to destroy the system? Yeah? So you need to design the invariants that hold true even when the environment is hostile. Okay? This is what is called adversarial analysis, the one that I show you with the diagram a while ago. Okay? So information asymmetrics, yeah, should be done before the transaction occurs. Yeah. Then it will cause the system participate in the pool that decrease the failure. Yeah, I give you example of what is called insurance debt spiral. Yeah, because you set a single average of the rule of the price. Okay, then it will create systemic failure. So look at this. This is classic example. Yeah, insurance debt spiral. Say The population, imagine you have population of 50 healthy user of your insurance. Say cost 1,000. And you have 56 user out of this. So you have cost 9,000. Okay. So the true average cost is becoming 5,000. Yeah. So if the system charges on average premium of 5,000, then the healthy user will refuse to pay. Yeah. And then they exit the system, the insurance. And then now the pool become 100% sick user. Yeah. So by creating you set the insurance price based on the average. Yeah, you're actually creating a system value. So, do you get the idea or not? Yeah. So you charge the average price of 5,000. Yeah, and then healthy people realize that they are being ripped off and leave. Yeah? The moment they leave, your average cost is no longer 5,000 anymore. It jumped to 9,000. Yeah, because only sick people will stay, and then you will go bankrupt as the insurance. Okay, so because healthy user refuse to pay 5,000 for 1,000 value, okay, and then they exit the system. Yeah? So now your pool become 100% sick person user. Okay, so how to fix this problem? Yeah. So to solve this problem, you need to do what is called adverse selection. Yeah, you need to do screening. Okay, so you will offer high deductible, low monthly cost, yeah, to the healthy people. Okay, so you don't set one value to all the same. Yeah? So you need to prevent the moral hazard. Okay, so don't offer average market salary because you cannot tell the difference between say 10x people and the lazy people. Yeah, say the best developer and the lazy people. If you put the average, okay, then the good people will go out of your system. Yeah? And then eventually only the lazy people will stay within your system. Yeah. So measure based on selection, meritocracy, right? Yeah. Based on what they actually produce or create productivity within your system. Okay. So this is another example of what is called civil attack. Yeah. So you want to create a democratic online voting system. Okay. Using one vote per IP address. So using this what you call democratic online voting. Okay. This is easily attacked. Yeah. So people can just pay say 500 US dollar to rent the botnet to create 100,000 IP address, and then they cast 100,000 vote. Okay, so then it's no longer democratic because those who can cheat, yeah, will win. So what is the solution? Yeah, so the solution is smart contract. Yeah, so similar to blockchain. Yeah, so you need to have a verifiable physical constraint. Yeah? So when you force the actor to burn real physical constraint like physical energy, yeah, that exactly in the blockchain, right? Or similar to Bitcoin. Yeah, so you need to pay very expensive energy. Yeah, in order to proof of work. Okay, then the architecture or the design will go to make it not good for those who cheat. Okay, and those who do correctly will get the reward. Okay. This is for urban planning, yeah, or transportation. Urban planning, yeah. So imagine you want to build a public plaza, say public park, okay, say in the neighborhood of 3 residential buildings. Okay, so the cost of building that public plaza, say 60,000, right? And then the cost is split equally, say 20,000 each. Okay, so the net valuation is 20,000 each. So then they need to have each of these resident will have their true valuation, right? So if you survey the resident, how much they value that public plaza, yeah, there is possibility that they will lie, right? So this is called free riding problem. Yeah, those who want it will underreport their valuation, hoping the other will pay for it this month. Yeah. There is also possibility of sabotage. Yeah. Those who don't want it will drastically exaggerate their negative valuation to kill the project. It happened, right? So as urban planner, you will face this kind of problem. So how to solve this problem? Yeah, there's two possibility. Yeah, one is free rider, the other one is sabotage. Okay, so you're asking them willingness to pay, right? But depending on willingness to pay can be sabotage, yeah, or free riding. So how to guarantee that they will not lie? This is the mathematic value. Yeah, so I put it into variables. So 60,000, 20,000, right? So the net valuation is supposed to be negative 20,000, right? So, say, example, yeah, resident A, B, C, yeah. So A true value is 30,000, B is 25,000, and C is actually losing over this 20,000, so 10. Okay, so then if you calculate the total, yeah, so 10 plus 5 plus negative 10, that will be positive, still positive, right? So that the net positive means that public park or the plaza should be built, right? But what happened is, if they know this transparent, if you put this transparently, so transparency is not necessarily a good thing. Yeah? So if you put this transparently, what will happen? The resident C will sabotage. Yeah? They will lie. They will say, okay, I will vote for negative 100,000, yeah, to guarantee that the project fails. Why? Because they don't want to pay 10,000, right? Yeah. So because they value only 10,000, right? So their net value is negative, so they don't want this project. So what to solve? How to solve this problem? Yeah, yeah. This problem has been solved, yeah, by these three person, yeah, Fikre, Clark, and Grove. So based on the name, so you know that this is quite important, yeah. So this is called VCG mechanism. Yeah, a little bit complicated. I hope you bear with me. Okay. So the technique is you only pay the tax equal to the externality you impose on others. Okay, you only pay a penalty, yeah, for your vote, okay, in that public part a while ago, that change the final outcomes. Yeah, this is actually holy grail of mechanism design, yeah, for public good. Okay, because it will isolate the user input from their direct costs. Yeah, it will break the incentive for underreport. Okay, so if your vote change the outcomes of the group, you need to pay, yeah, the exact financial damage that you cause. Okay, so let's look at the math, yeah, in the next slide. Yeah, so we will apply what is called Fickrey-Clark growth mechanism. Yeah, so it's the same as before. Everyone will report their value on that public bar, well, yeah, public goods. So the project is built if the total value is more than the cost, right? So the project will proceed if the sum of all reported valuation is positive. Now, you will impose, this is the rule, yeah, you will impose penalty tax, yeah. You only pay the externality that you impose on others. That's the rule, yeah. So a resident will pay a penalty tax only if their vote is called pivotal. That means it will change the outcomes for everyone else. Okay, and that tax equal to the damage that they did to the others. Okay, as the result of this, yeah, honesty becomes strictly dominant, mass equilibrium. Okay, so the clock tax will force people to be honest. Okay, so how to do this? Yeah, say example, if the resident C a while ago lies and report say minus 20,000, yeah, the total drop will become minus 5,000. The project is cancelled, isn't it? Right? So because resident C changed the outcomes from 15K without them to be cancelled. Yeah, so it changed the outcome. Then the C is taxed for the exact loss utility for A and B. Yeah, so that is 10 and 5. And the total is 15. So if if C lies, yeah, no plaza is 0, and minus 15 is the tax, become negative 15. Okay, if he tell the truth, okay, the plaza is built, and they need to pay the sharing, which is 20,000 share for that 10K plaza, the net still negative 10. So negative 10 compared to negative 15, yeah, negative 15 is worse. In that case, they will tell the truth, isn't it? Yeah. So because losing 10,000 is mathematically better off than losing 15,000. Okay. So then even if C is selfish, okay, then the rational move is to tell the exact truth. Yeah. So this is the perfectly incentive compatible. Okay, up to here, is there any question? Nice, no? This mechanism. Yeah. So you probably can introduce this. Yeah. I'm not sure if this has been in the practice in the Philippines, but certainly in the other part of the world, this has been being used for public good. Okay. Any question, comment, discussion before we go to the next? So in this next part. This is the last part. Okay. So I want to discuss about more advanced system control and market design. So when we said market design, it's not always about money. Sometimes market is not necessarily related to price or income. So here it is. So we have term what is called incentive compatibility, right? So it is a systemic invariance ensuring that the actor, even if it is the most selfish but rational, will align with the global optimum state. So a mechanism is called incentive compatible. If every participant achieve their mathematical optimal payoff strictly by adhering the system rule. That means they will tell the truth. Okay, so you can eliminate mathematically, the lying mechanism. There are many technique of incentive compatibility. One is the congestion pricing. This is not about truth telling, but about the systemic payoff. Figure option and honest ranking in Kale Shipley is about truth telling. Okay, so the point is you cannot rely on trust and altruism or compliance. Okay, so you need to engineer the payoff matrix. So that the hiding the truth or cheating is actually less profitable than playing by the honest things. Okay, so in transport we have what is called Brace paradox. Okay, so user equilibrium is basically Nash equilibrium. Driver will selfishly choose their fastest route. Okay, so because of this, congestion happen. What is the system optimum? The system optimum is the routing that actually minimizes the total network delay. Brace paradox is a paradox that adding new fast shortcut will make everyone commute slower. Okay. So say the original baseline, say you have 65 minutes, example. And then you add new shortcut around. The network capacity increase. But the average delay actually also increase. What happened? Why that happened? The root cause is because of Nash equilibrium. Okay, so people will do selfish routing, to divert from the system optimum. So driver do not pay for the delay they inflict on the others, right? So then what is the solution of this? The solution is actually congestion pricing. So you create toll, similar to Singapore IRP system. So you charge the toll exactly equal to the delay that the driver costs for everyone else. Okay, so this will force the driver to internalize their costs, into the choice, the selfish choice, isn't it? And then it will align to the optimum system flow. Okay, so if you enter a highway and you do not pay for the, say, 5-second delay, that you will cost for all other car that behind you, then because the cost is zero, the road is overconsumed, right? By introducing congestion pricing, in real time, so you create a feedback loop. So the driver will be forced to think their costs that they inflict on the system. Then it will shift the demand, yeah, based on time and space to match the actual capacity of the road. Okay, so of course this is a little bit more complex here, but introducing this kind of complex multi-agent network failure, yeah, where the NAS equilibrium is actually going toward the system optimum, okay, then you will have a better system. Yeah. So next, I want to introduce you with Fickrey option. Yeah, the same Fickrey of VCG a while ago. Yeah. So this one is used for bidding. Okay. So in this kind of bidding, imagine you want to get the highest value, yeah, not the lowest. When you want to get the lowest, that means a reverse bidding. Yeah. So Fickrey auction, okay, already used in Google and Meta. Yeah. Say you want to bid for the advertising value, they use Fickrey auction. Yeah. What is Fickrey auction? Yeah. This is called second price seal bid. Okay. So you want to sell a project contract. Yeah. For example, the spectrum frequency, for example. Yeah. So the bidder will submit the seal bid. Okay. And then the highest bidder will win the item. But they will pay the price of the second highest bid. Okay. Why? Okay. If you bid less than your true valuation, yeah, you lose, you have a risk to lose the item that you want because someone else will value less than you do. Yeah. And if you bid more, you risk winning but paying more than it worth. So in that case, okay, the best strategy for you is based on this Fickrey auction is to evaluate, yeah, to value the true value. Yeah, honesty is the best strategy. So by doing this, you will have mathematically, yeah, forced total honesty. Yeah. This is the example in numerical value. Say there is one project with two bidder. Okay, so the bidder one value the project say 20. Yeah, and then bidder two will value the project at 5. Okay, of course the city will use the first. If the city use the first price auction, the bidder one can guess what bidder two will bid. Okay, so if bidder one guess 4 million, they will just bid 4.01. So then, and if they guess wrong, of course, they lose the project. Yeah, so this will create underbidding if you use first price auction. By Fickrey auction, you not use the first price auction, you will use the second price auction. Okay. In this case, the mechanism is something like this. Yeah. So both bidder will submit seal bid. Okay. Again, the highest bidder still wins the spot. But the rule is the winner will pay the price of the second highest bid. Okay. So the bidder one, say bid their true value, say 20, bidder two also bid their true value 5. Okay, bidder one win, but only charge for 5. Why the second price? Yeah, because it will completely decouple the bidding from the price paid. Yeah, overbidding risks paying more the spot worth, and underbidding will lose the spot. Okay, by doing Fickrey auction, okay, so the computationally dominant strategy or the NAS equilibrium is for the bidder to simply tell their exact true value. Okay, so apply this to urban planning. Say you want to sell a spectrum run or public land, right? If you use first price auction, the winner pay what they bid, right? So then they will underbid. Yeah? Okay. So using Fikri auction, the winner will pay the second highest bid. Okay. With using this, okay, they will bid their true value. Okay. So the standard auction will fail because the bidder will try to bid the system by guessing what other will bid. Yeah, leading to loss of public revenue. Okay, using Fikri auction, we change just one rule. Yeah? The winner will pay the second highest price. This is a twist. Yeah, instantly remove all the incentive to lie. Okay, why? Because it decoupled the bidding from the final price that they pay. Yeah, removing the bidding mechanism from the price. Okay. So, and this has been used, yeah. So Google and Meta Ads are actually using this mechanism a lot, yeah, for their advertising. Okay. Any question? Any discussion about this? No? Okay. So let's talk about extortion problem. Yeah. So say city want to buy parcel lots, say 3 adjacent parcel of lot. Okay. And if you do it sequentially, for example, you want to build a road, yeah, and then you want to buy the land, right? For land acquisition of the road. Yeah. So if say for transit hub, so, yeah. So if you buy in sequential, say the city will buy parcel 1 and then parcel 2. Yeah. The owner of parcel 3 will realize that the city is trapped. They already bought the land. They will buy this transit hub for the transit hub. Then they will demand higher price. Okay, they will demand higher price than the work. Then the project will collapse. Yeah, this is called extortion problem. Yeah. So what will happen? What can we do about this? Yeah. So the design mechanism is to create what is called dominant assurance contract. Okay. So the city or you as a planner, okay, will make simultaneous offer to everyone will with strict contingency. You say like this, even if one of you say no, yeah, one for all, yeah. If one of you say no to this project, okay, we will void the contract, okay, and then we will not build this here. We will build somewhere else. Okay, so by doing so, suddenly the last landowner cannot demand more money because if they say no, they will ruin the deal, isn't it? So yeah, so then rejecting is no longer the nice equilibrium. Okay, hold out problem is become vulnerability in sequential negotiation, right? So if owner 3 using this SIF, yeah, will no longer exploit the city. Okay. There's in mechanism design, there is a principle called revelation principle. What is this? Yeah, this is one of the most powerful theorem in mechanism design. Yeah. So revelation principle dictate that you must change the direct input mechanism. Yeah, you must change into direct input mechanism. Yeah. So instead of handling indirect, you need to use direct reporting. Okay. So yeah, similar to a Fikre style algorithm a while ago. Okay. Instead of multiple bidding round and a lot of guessing, so you can just use Fikre auction a while ago. Yeah, directly telling the truth. Okay. Uh, Last but not least concept that I want to introduce is called market design. So remember this. When you deal with public school choice, medical residency, organ donation, for example, then you cannot use money, right, to solve the allocation problem, right? So how are we deal with economic that do not have certain price? Okay, so price alone is not the standard here. Then what you need to do is to create algorithm. Yeah, we will use algorithm. Yes, for example, stable merits, Gale Shapley. Yeah. So when the price is removed from the equation, okay, you still can clear the market, allocate the resources. Okay. Before that, you need to understand what is the meaning of market. Yeah. What is the meaning of functional market? So there are three invariants, design principle, okay, that create market. Yeah, market is not natural phenomenon. Okay, it is a system governed by rule. Okay, so you need to have these three in order to create market. Okay, number one, if you want to create market, you need to have what is called thickness. Yeah, so you need to have enough participant to find the match. Yeah. So these are the examples. So if you want to create dating app, so you need to have certain number of users. Yeah. So second, to create a functional market, you need to have safety. Yeah. It is safe to reveal the true preference. You will not get punishment by telling the truth. Okay. The third one is overcoming the congestion. That means the system will process the transaction before the deadline, before there is a timeout. Yeah. So in the organ donor example later, you will see this. Yeah. So this is one example. Okay. Say in the flood insurance a while ago, in the example of flood insurance a while ago. So if only one homeowner maintain the drainage, yeah, then the system is not thick enough to prevent the collapse. Yeah. Second, talking about the safety. If the homeowner feel punished for spending the money while the other get freeloading, yeah, then they will stop revealing the true preference, isn't it? The third one is congestion. So that means if the government cannot process the claim quickly, then the system will clog and collapse. Yeah. So the three market condition, the thickness, safety, and uncongested is important. Yeah. So there is a algorithm called stable merit, yeah, that we can use, yeah, for creating this kind of market. Say example, yeah, you have 3 hospital, 3 doctor. Okay. So and the doctor and the hospital is under panic and timing pressure. because it's unregulated, then it will cause panic. Okay, so for example, Dr. A prefer hospital A, but will accept C because of panic, yeah, causing a fear. Okay, and actually this one also prefer B and C prefer C, hospital C, but all will be misaligned, yeah, because there's possibility that Dr. A end up in hospital C, yeah, even though both uh, Dr. A and hospital A is actually prefer each other. Okay, so what is the solution of this? Yeah? The solution of this is each doctor will submit honest list of rank. Yeah? And then each hospital is also submit the rank list. And then you can use the algorithm, it's called uh, Gale-Shapley algorithm. Yeah, Gale-Shapley, or I think I put it here, right? The Gale-Shapley algorithm to create a matching between the doctor and the hospital, yeah, so that it will be assigned correctly. So what we have here, we move from just design mechanism that creates Nash equilibrium into another kind of design mechanism that use algorithm. Yeah, this is more advanced. Yeah. So another example here is the kidney exchange, right? So in the kidney exchange, this is to demonstrate how you build a mechanism of design mechanism, okay, where the money is strictly illegal if you do transaction. Yeah, you cannot buy or sell kidney, right? So then you remove the price out of the market. So, but we still can do market design. Yeah. So what to do? Yeah. So in this case, you solve this using cyclical exchange. Yeah. So the mechanism will look for the entire database of incompatible pair. Yeah. And then it will find a chain. Yeah. Donor A kidney is biologically compatible to patient B. Yeah. Donor B is compatible to patient C. Donor C compatible to patient A. So become a cycle. Yeah. So because of this kind of algorithm that execute multi-party swap simultaneously, okay, then you will have maximized total number of life saved. Yeah. And you still clear the market, without any exchange of money, without single dollar. Okay. So the point is now we create a mechanism design, yeah, based on rule or algorithm with this exchange of cycle, yeah, to maximize the welfare under the legal constraint. Yeah? You cannot buy or sell kidney. Okay. As conclusion, yeah, or the summary, yeah. So remember, yeah, we have a lot of coverage today. Okay. So I hope you design, yeah, certain things within your limitation. Okay. So in that case, you need to assume something. Yeah. Assume that everyone is selfish. Yeah. Do not rely on goodwill or memory. Okay. And you can create paranoid threat modeling, and then you reverse the direction of control. Yeah. So I put also there in the slide. Okay. If you want to talk about how are we going to deal with corruption and collusion. Yeah. So these are example of a technique that you can also use. Okay. So at the end, I hope you can create better family, better office, better nation, better company, yeah, better society, yeah, by doing all of this. Yeah. So okay. Is there any question or discussion about mechanism design? Yeah, so if not, you can present your group project. So who will present first? Yes, of course.
Sir, it's only 10 minutes before 9, sir.
Oh.
Can we still present these 3 groups for 10 minutes?
How long you can present? Oh, you want to present next week?
I don't know with the other groups, sir, if they want next week or now. But now it's only 9 minutes. But it's okay. If you
Yeah,
want
it's
us to
okay.
present, then we can
No,
present, sir.
it's up to you. You decide. No problem. I can either with today or next week. That's fine with me. If next week you can even revise. If only 10 minutes, yeah. Okay, so you can
Okay,
present next week, so we can discuss more detail about this today. Is that okay? In 10 minutes? Or you want to present it today? Or some of you will present today and some of you will present next week. That's okay.
okay, sir. I will try to present today, sir.
Okay,
Our group.
cool. I will stop sharing and you can present. Time is yours. Are you still there? Oh, okay. I think you are muted.
Is it okay, sir? Is it okay now? Okay. Okay, good evening, everyone. So we are Group 2. The title is an optimization approach to illegal parking management in Quezon City. So, so for this presentation, we will just discuss the revisions that we made based on the comments from our previous presentation. So we improve our strongly connected network because you have, sir, a comment for that one. Then we also revised the values used in the optimization model, particularly the CCTV decision variable. Previously, we have 20,000. Okay, later I will discuss this one in the following slides. For multi-criteria decision-making methods, we also add some sensitivity analysis for the IFN softmax function by varying the gamma value from 1 to 5, 10, and -1. Then we also add this risk and opportunity loss assessment in part 6. Then finally, for part 7, we do sensitivity analysis using the Eurowix criterion to further evaluate the robustness of our results. So problem statement, you already discussed this one previously.
Oh.
So
wait. They cannot see your screen. I don't know why. How to make? Maybe I will set you as co-host. Okay. Can you see George screen? Okay. Good. Sorry. Go.
okay. So the problem statement we already discussed this one in, I think in 2 previous presentations. I will just skip this problem statement. So for a strongly connected network, we have the agents, the LGU the traffic enforcers, motorists, local business, and residents and community. So for factors, operational variable, the enforcement hours, the same as previously that we presented. Okay, so this is now the revised strongly
Okay.
connected network. So so this illustrates the relationship and influence among key stakeholders in illegal parking management. So in this network, we also put some legends so to make it clear. So as shown in the upper left, the arrows represent the strength of influence among stakeholders. So we put red arrow indicates strong influence. The blue arrow indicates moderate influence. The dash orange arrow indicates a weak influence. Then at the center of this network is the LGU or the Traffic Management Office. So this one has a strong influence over traffic enforcers. So how? Through policies, regulations, and budget allocation. So the traffic enforcers also have a moderate influence back to the LGU. So it's only moderate as they provide reports and feedback on operations. Then in turn, yung traffic enforcers strongly influence motorists through enforcement, monitoring, and penalties. And motorists directly affect businesses through their parking behavior. So why it's parking behavior? Because the motorist behavior influences the customer access to business establishments. Also, the delivery flow of goods and services and overall traffic conditions. So with this behavior, this may affect the business income and accessibility. So businesses also have a moderate influence on the LGU. So as they contribute to the city's economic development. So in addition, the businesses moderately influence residents and the community by providing employment, goods, services, and overall economic support. So residents, on the other hand, play an important role by having a strong influence on the LGU. So through public pressure, feedback, and most especially voting power. Like during election, the voting power of residents has major influence or impact to the LGU.
Mm.
So their level also of public satisfaction, such as the
Okay.
trust, traffic quality, and safety, also affects the LGU. So this is the whole strongly connected network, sir, for our project.
Can I give comment first? If
Okay, sir.
it's okay?
Yes,
Can
sir.
I interrupt you? Okay, so later on you can just put number here. Yeah? Weak influence, for example, you put 1 or 2. Yeah, moderate maybe you can put 3,
Okay, sir.
4 like that, and then strongly influence you can put higher number. Okay, and
Yes, sir.
then what will be your target? Yeah, so you want to put, for example, the residents or community supposed to be the highest power, right?
Okay.
Correct. So in
Yes,
that
sir.
case, check whether this is actually true. Yeah, so you can put these numbers, put this into matrix, and then you put into, I think, power dynamics calculator
Yes, sir.
in the
Actually, this is the power dynamics, which I have to
yes,
ask
yes.
actually, sir, because we haven't discussed yet this
We
power
haven't
dynamics.
discussed yet,
But
but
we watch partially the video
yes, yes.
that you sent
So
us.
once you put that, okay, you supposed to get suppose, yeah, the
Yeah.
resident is not supposed to be the highest power. But if it is not, then something wrong with your structure or something wrong with your numbers here.
Yes, sir.
Okay, so then you need
Okay.
to revise. Is that okay?
Okay, sir.
Okay, sorry. Please continue.
Okay, for this optimization model, the same objective
This
function
is
to
fine.
maximize this one. So same as what we have presented before, we didn't change anything.
Okay.
So I will just, but this is the comment, sir, in previous presentation
The value.
about the CCTV unit, which is
Last time was
20,000 before. Now we reduce that value into 10,000. Actually, this 10,000 will cover the maintenance cost, the electricity, the payment for monitoring personnel, the system operation cost, site-related installation support,
Can you put the
something.
unit? Is this per year or per month?
This
or
is actually the
monthly?
daily cost, sir. For yeah.
Daily cost is 10,000.
Yeah, as what I have mentioned, sir, this is for like payment for monitoring personnel, the electricity
see.
cost, the maintenance, the system operation cost,
Okay.
site-related installation. So we instead of 20,000, so we reduce half, which is
Okay.
10,000. So our equation for this budget constraint is this one, not equal or less than 350,000. So the same amount for manpower, 24 hours, for physical curb space 30, then 12, 5, and all non-negativity constraint is 0.
So where did you come with the number 350,000 come from?
This is our assumption, sir. A realistic assumption that this will be the total budget that the LGU can provide for this particular project.
And if you can get literature from this, that's better. Okay.
Okay, sir.
Next.
So this is now the we rerun after we changed that value for CCTV. So we rerun again the linear programming. So this is now the result. So the see now previously it's 300. Now it's 640 46. So remain the x1 to x4 variables remains the same. But they are used at their maximum level. So x1 24, x2 30, x3 12, and x4 5. So this means that all enforcement, core space regulation, the towing, and CCTV are fully utilized and contribute to our objective. So this one, we also have the shadow price constraint analysis. I will not discuss this all. Also this one, the RHS. Then we do some interpretation.
Okay.
Then these adjustable cells, we also do some interpretation. Same criteria and alternatives that we have presented before. Same ranking of this one. But this one, we added this ideal flow network IFN by increasing this gamma. Before it's only the gamma is 1. So now sensitivity analysis, we make gamma into 5, 10, but same ranking. But when we do this -1, then the ranking is reversed.
Yeah, of course.
Yeah. So for comparative analysis, we also presented this one. So the new additional information is this risk and opportunity loss. So we make this analysis using the gain payoff matrix and Savage minimax regret rule. So at the top, we show this gain payoff matrix. So each alternative is evaluated under 3 possible states of nature. We put high success, then N2 is moderate success, then low success. So these values in the payoff matrix represent the estimated level of effectiveness. Actually, these values are not random. So we base this from our optimization results, like the effectiveness and realistic assumption. So for example, this curb space regulation, we put highest value because it directly controls road space and prevent illegal parking physically. Then the enforcement CCTV, moderate values, towing and penalty, lower values. So we computed the regret matrix by subtracting each value from the best possible outcome per column. Like for example, the N1, the best value is 150, for N2 110, N3 70. So to get the regret matrix, we subtract best minus the actual. So this is now the value on the lower table.
Okay.
So using the minimax regret rule, we then identify the alternative with the lowest maximum regret. For example, the alternative A, we have 30, 0, 50, 60, 70.
Skip the process.
Yeah, then 0. Yes. Then based on this illustration, this is now the decision is we need to choose B alternative, which is the curve space. That's the lowest worst case regret. Now for desensitivity analysis using the Hurwitz rule, the alpha 0, 0.5, and 1. So from the alternatives, we get the best value, then the worst, or the maximum gain, or the minimum gain. Then we computed using this formula, the Hurwitz equals alpha times max plus 1 minus, then this is the result of the alternative. So based on this one, the best option is alternative B for all this value of alpha.
Okay.
That's also for our presentation.
Okay, so can you add, for example, we discussed a lot about game theory and mechanism design. Probably if you
Yes.
can touch this one also. Yeah.
Yes, sir. Yes, sir.
Okay. And
Okay.
financially you already did so. Okay. So thank you, George.
Thank you, sir.
Yeah. So for the other group, do you want to present it next week? Or you want to present it today? Maybe next week is better. Some of you are very hungry. Yeah. So thank you very much for today. Yes. Yes. Okay. No problem. So next week. Yeah. So you can even update. Yeah. So if it is still incomplete. Yeah. Thank you very much. So See you next week. We will discuss about the IFN, power dynamic, and group decision making. And I will answer Mr. Ando question.
Sir, sir,
Yes.
uh, sir, in the Revolido, I check it. The submission for power dynamics is this coming May 7. So do we
Okay,
need to answer
so
it, or we
I
will just
think
wait?
I think I can yeah. You remind me which one is incorrect. I will fix that because I don't
Okay,
have
sir.
any report in Revolido where is correct or not. So I will check. Yeah. Thank you very much for your feedback. Okay. Okay. Thank you. So
Okay,
see
sir.
you
Thank you, sir. Bye, sir.
next week. I'll post this one. Yeah.